All right, in today's notes, we're going to talk more about parts of circles. We've already introduced chords and arcs, but today we're going to talk about some properties that these things have. So as a reminder, a chord is simply a segment that starts and ends somewhere on the circle. It could be short, it could be long, it could be a diameter if it goes through the center, but a chord is just any connection of 2 points on the circle. So two chords are congruent if and only if. So basically, looking at it in terms of the chord and the arc that it forms, so like this chord AB forms arc AB. So what it's saying here is that the chords are congruent. So like AB and DC are congruent only if CD, the arc, and AB, the arc, are congruent. So those segments and their matching arcs are congruent together. And since it says if and only if, that's a biconditional, meaning that it works in both directions. So the chords are congruent, so let's just say that means segment AB is congruent to segment CD if and only if, so that's our bidirectional arrow. And then we're going to match that with the arcs. So arc AB is congruent to arc CD. So in the blank A here, I guess what I wrote here goes with the arrow right here. So you can fill it in that blank if you like. And then in words it was two chords are congruent if and only if they're, I guess, subtended, or their arcs are congruent. I think that this is where we would use the word that this arc is subtended by that chord, or maybe you can only have an arc subtended by an angle. I don't know. I'm not that big on that word. It's a weird word. I'll try to use it appropriately if I can. I didn't even spell it right. Wow, terrible. Subtended. So like sub, like below, and tended, like you're tending to something. So that is one way that we know they're congruent. If we have two congruent chords, then or two congruent arc lengths, then we have two congruent chords. Or the other way we know is if the two chords are equidistant from the center point. So I'm going to write that one as the biconditional here. So it would be AB chord is congruent to CD if and only if the distance from the center is the same. So that would be here EF, no segment notation because it's a distance, is equal to EG. I mean, I guess we could call those segments as well, but since they are drawn here, but I was just going to say equidistant, so we could say EF equals EG, or EF is congruent to EG. Same thing, like equal length or measures are equal. That's basically the premise here, and the important thing to remember is how we know when chords are equal. Either we know they're the same distance from the center, or we know that their arcs match. So to prove these things, you would use like triangles or maybe kites. So if I were to draw the radii to the end points of these arcs, we know that those radii are equal. So then if we know, we have related the central angle, so like this angle here, to the arc measure, right? So we know that if AB is equal to CD, that these two central angles are congruent. Then we know that these green triangles are both isosceles triangles because they both include two legs that are radii of the circle. So that means that the two segments must be equal because by side angle side, we have congruence between those two triangles. So that's how we get to AB congruent to CD. Is a lot of these proofs and a lot of the way we think about these things involves auxiliary lines often those lines are going to be radii, because radii are always equal in length, so they let us establish these kind of properties. Then within those triangles, we can again see that if we draw our altitudes, because we know that altitudes of congruent triangles are going to be congruent, so we know that this and this are congruent as well. So we could use the lengths of those altitudes, these radii, and those central angles to prove these two things to ourselves. But all we really need to do is remember those rules. If you want to make proofs of them, you draw those extra things. So what is this one? So if a diameter or radius is perpendicular to a chord, as the ones drawn here are, then they always bisect the chord and the angle. I don't know which of those is supposed to go in the first blank, but whatever. Chord and angle. So think about my orange line here, my altitude that we were just talking about from the center extending out like a ray. It's going to always split this segment into two equal parts and this arc into two equal parts. So again, that's just the nature of these triangles, that you could establish these two triangles are congruent. So AFE and EFB would be congruent because this is equal, EF is equal to itself by the reflexive property. So again, we get side angle side between these two smaller triangles, meaning that this is bisected. And then since that's bisected, so is the arc. So we kind of get this nice little package where everything is nicely related to each other. So how would we write that as a biconditional? So we would say if EF is perpendicular to AB, then we know that AF equals FB. So that would be the segments. And we know the measure of arc AH is equal to the measure of arc HB. And here I'm using measure of arc to represent, I guess, both the angle measure and the length. Maybe it's better to, like I did up here, say that the arc is congruent to the other arc. But like I said in the last video, I don't really have a good way of representing arc measure versus arc length in notation. So if I use measure of arc whatever, I mean, just assume it's talking about both because they go hand in hand. Let's see if we can use some of these properties to solve some problems. So it says to find x. X is up here in this expression. Since these are degree measures, right here it says degrees and here it says degrees, I know that we're measuring the arc measure of ST and the arc measure of SR. So we know that these two chords are congruent. So we're going to use the property that if two chords are congruent, then their arc measures and arc lengths are congruent as well. So we know that 115 degrees equals 7x plus 24 degrees, because if these are equal, their arcs are equal. So subtracting 24, we would get 91 equals 7x, so x is going to be 13. And that's all there is to that. So it's just a matter of knowing that property and applying it. And whenever we see two chords drawn in a problem, we should be thinking we're probably going to be using this chord property definition of equal chords. This one says find x. We know the arcs are equal, so that also of course means the two chords are equal because these chords form those arcs. So it is very important that we're matching up this, the endpoints of this chord are the endpoints of that arc. So we can do 52 equals 18x minus 2. That gives us 54 equals 18x and x equals 3. This one wants us to find the length of xy. So we know we need to plug x back in. It's not just finding x, we're going to have to substitute it. but otherwise it's the same as previously. We know these two chords and their included arcs. So we know 9x minus 34 is equal to 4x plus 1. That gives us 35 equals 5x when we move our terms around, and x equals 7. But make sure we're not done there. We need to take that 7, plug it back in, and find the length of xy. So this is a good way just to check your algebra anyways. If we plug in 7 here, we get 29, and if we plug in 7 here, we get 63 minus 34 is also 29. So that's good. They turn out to be equal. We could have done that here as well, plug in the 13, and get 91 plus 24 is 115. So remember, algebra you can use to check itself. Okay, find measure of arc RS. So in this case, they're talking about degree measures, so I'm going to find my answer in degrees. If we were talking about lengths based on context, I would find the length of the arc. Right, so we know RS and PQ are congruent, so these two arcs are congruent. So we can set up 5x plus 6 equals 11x minus 72. We get 78 equals 6x, so x is 13. And then we want to find the arc measure, so we plug 13 back in. 13 times 11 is 143 minus 72. So measure of arc RS is going to be, I guess here I could have put xy equals, measure of angle RS is going to be equal to 71 degrees. And we will include degrees. X was not in degrees because it's in the parentheses, but the arc measure should have a degree symbol. So that's the basic properties of our notes for today. There's this page after that that goes and kind of makes it even more explicit. It's the same stuff though. So it's talking about the same properties that we talked about above, other than it's basically presenting these perpendicular lines as perpendicular bisectors, which we didn't use that terminology in the last slide or last page. But this is all the same properties we just talked about, written out with a lot of words. I tend to prefer the symbolic definitions, so these if and only if statements, those to me are more meaningful and easier to remember than a paragraph of text. But if you like text, this is defining the same kind of stuff. So I'll do a couple more practice. That's really all there is for today's notes. There's several practice pages to look at. So page 16 and 15 here are good practice. I'll do a couple more practice problems, but if you think this seems really straightforward, then feel free to go ahead and just work on the practice. Oh wait, one more thing. So if you're going to turn off the video now, I wanted to mention, you can kind of see it from what I drew here, but I want us to look in these circles for hidden shapes. So we found some hidden triangles there, but I want us to note that if you draw a perpendicular bisector through a chord, so we have this right here, another way to think of it besides the triangles is this shape, if we kind of connect our vertices, is always going to form a kite. So we know about kites, and we know that this diagonal is always bisecting the other one. So that's another way to think of AF equals FB, is by connecting the dots and making a kite shape here. Then we know that that's going to be equal. Okay, so now if you want to go work on practice on your own, go for it. I'm going to do a couple more examples in case you need a little more support. So here we've got circle Z, so defined by its center point. RS, that's a chord, is equal to 18. And the measure of arc TY, so they're giving us just part of the total arc here, is 42. So we're going to use some of our relationships here. RS, we know, is double these two. So if they ask us for RW and WS, that's how we'll find those. We know TY is half of TU, so that'll be a way to find those. Then we know that since we're given right here, these chords are equidistant from the center. That also means that RS is congruent to TU, and arc RS is congruent to arc TU. So that should allow us to find like all the stuff we need using those relationships. So let's go through and see what they're actually asking for. First of all, TV, we just said, is going to be the same as a half segment here. So since RW is 9, so is TV. TU is the same as RS, so that's the full 18. WS is another half of a chord, so that's 9. Measure of arc YU is going to match this one, so that's another 42 degrees. And measure of arc RS is going to equal TU, so that would be 84 degrees. So all of these things just matching up what's equivalent, but I do want you to keep in mind that what lets us do that, the thing that allows us to do any of that, is this congruent marking. Without that there, we wouldn't have enough information to relate this chord in this one or this arc in that one. This is kind of what ties it all together and allows us to do the math, the equivalencies that we're doing. Okay, so circle I, so again naming by the center, we have, again, equidistant chords. Here they happen to run into each other, that doesn't matter at all. But we know that these two are equidistant, meaning BC and BA are the same. So here, where it asks for BC, my question is, how long is BA? Or how long is BG is what they give us. So they give us BG is 17, so BC in total would be double that, or 34. Next thing they ask for is FB. That's the same as BG, because it's a half of one of the chords, so it's also 17. Measure of arc AB, that's going to be, so they gave us CHA. That's interesting. They gave us the long way around. So remember that is the major arc rather than the minor arc. So if that one is 256 degrees, then what's left for our two arcs over here is 360 minus that, which is going to be 104 degrees. That means each BC and AB are half of that, which is, so divide by 2, we get 52 degrees. So now I can answer measure of AB is going to be 52 degrees. And measure of BC is equal to 52 degrees as well. So if I was asking here, what measure does it mean, angle or length? One way I can tell that is I have no way of determining the length because I don't know the length of the radius. Remember that to go from arc measure, which is degrees, to arc length, we need to know the circumference. So without a radius or a diameter, we don't have any way of actually finding the arc length of BC. I think that's true. Maybe that's not true. I'm going to go with it. Okay, measure of arc EC is half of one of these two arcs, so that would be 52 over 2, or 26 degrees. So that's that one. Let's see. We'll do 7 and 8 to wrap up the video. Maybe we should do this one. It has a funny picture. We'll do a couple more. I mean, like I said, if you want to stop the video, you can. So I'm going to keep going in case you're still confused about anything. So QM, which is half of one of our chords. Again, we have these two equal markings, so we know the chords match. QM is half of a chord. MR is half of a chord, so they are congruent. So we're going to do 6x minus 11 equals 2x plus 9. We get 4x equals 20, x equals 5. That's not what they're asking for. They're asking for MN. So if MR is 5 and MQ is 5, MN, the total chord, would be double that. So MN is equal to 10. Here we have measure of arc CI, so that's half of our arc. Again, I'm checking for these marks to make sure we can actually relate the two to each other. Measure of arc EF, that's the total arc here, so that's twice as long as CI. So what I would do is say 2 times CI, right, because there's 2 of those, is the same as EF. You could also have done this is equal to 1/2 of that. That would work out pretty well since these are both even. So to solve, I'm going to start by, instead of distributing, I'm going to divide by 2 and get 7x minus 15 equals 6x minus 4. That gives me x equals 11. And they said find a measure of arc CI. So measure of arc CI is going to be plugging in 11 here. So that's 77 minus 15 is going to be 62 degrees. All right, and then this one has kind of a different looking picture from the others we've seen, so I want to take a look at this as well. There's lots of ways we can take these properties and then extend them beyond just what we've done here. So remember that we can use this stuff in conjunction with triangles, kites, and all the other stuff we know about. Probably not parallel lines unless the chords are parallel, but that's probably not going to be an issue. Okay, so we're answering find VW. So VW is this total chord length. We know that this is bisecting the chord because it's perpendicular to it. So that's the important property here, is we know these two are equal. The next important thing is this is a right triangle, and it's a Pythagorean triple, 5, 12, 13. So VW is 12 times 2, or 24. And then it says find measure of arc YW. So YW is this arc right here. What do we know for that? We know that it's going to be half of VW. So we're going... I don't see a way to solve this without trig. If there is one, I'm missing it. But what I see is this central angle is equal to measure of arc YW. So I think I would probably just plug this in the calculator to find measure of angle X, this central angle. And since I know all the sides of the right triangle, I could use any of my trig ratios. I'm going to just pick tangent and say tangent of X is equal to 12 over 5. And then I would do X is the arctangent of 12 over 5 and plug that in a calculator if we were doing a rounded answer. If you wanted a precise answer, this would be it. If we wanted to round it, we would do the calculator. Let me grab that real quick. Okay, I got my Desmos calculator, and we're going to do arctangent of 12 over 5. So about 67.4 degrees if we wanted a rounded answer for that. So measure of YW, I already forgot the number, is about, so it's not precisely that, and it was 67.4 degrees. That's it. So, like I said, after all of these ones, since we just did this whole page together, there's this other practice page. So try these, see if you're able to figure all of them. Hopefully you can use those rules we talked about and refer back up here if you forget anything.